Hello, can you hear me?
Okay, ma'am. I am available.
Hmm.
Uh,
So your
one
question
question,
start.
ma'am. Again, I will tell. Which of the following will
No, I
have the
understand your question.
highest isomer shift value? Fe F2 A option, B option FeCl2,
Hmm.
C option FeBr2, D option FeI2.
Okay. I think
Actually, electron negativity of fluoride is more
right,
compared than other halide complex.
right.
So in FeF2, d electron concentration is lower. D electron concentration is lower. So automatically the shielding will be decreases. So automatically the isomeric effect will be decrease.
Right.
Isomer shift will be decrease.
But it would be more negative, right?
Yes, ma'am. I think D option is correct, but in assignment solution given, F2 is correct. They given.
So the my question is like in the question, what have they asked? Like which one of the following is going to have more isomeric shift? Just that one.
Yes, ma'am.
So maybe see if you will consider the option over here, iron F2, Cl2, Br2, and I2. Now out of which of the following they are talking about whether it is negative they are talking about or the positive they are talking about, because it's a relative value, right? So out of the four, if we consider the iron F2, iron F being more electronegative in nature, that would be having more negative value. So the more delta negative value could be one possible factor that okay, it is having more value. That's why they might have given the first option, but I will get it confirmed with the professor, like whether it was being asked as a relative negative value or a relative positive value. Because if the question says like it is more positive in nature, then iron I2 would be the answer. If it is more negative, then it is iron F2 would be the answer. So you understand, like both the options could be possibly correct if the question has been framed in that particular manner. And if in the question it has not been clarified that which one of the following, like whether they are talking about the more negative or more positive, then there would be a doubt. So I will get it confirmed. Your concept is right, like which because of all the fluorine, bromine, and iodine, since iron is in plus 2 oxidation state, and this F2Cl2 Br2 seems to be like only two fluorines or bromines are attached. It is not like this. It actually occurs in a octahedral geometry, right? So here we generally would be having iron Sa and then F here, F here. So it would be kind of this geometry where the charge is balanced and it's an extended structure over here. So when iron is in same oxidation state, only the effect left is the F, Br, Cl, and I. And also you need to see the electrochemical series also. Which one is the weak ligand, which one is the more stronger ligand. Compared to iron, chlorine, bromine, if you see iron iodide being the more weakest ligand compared to bromide, then Cl, then iron. I'm talking about the weak ligand. So weaker the ligand, they would be having less interaction with your system, and the d electron density would be more. When d electron density is more, that would be giving you more shielding, less negative value would become. So you're understanding my point. There could be question regarding more negative relative to the other one, or it is being asked more positive relative to the other. So both the options could be right if the question is framed correctly.
Ma'am, iodide is a weak ligand compared
Right,
than bromide, chloride, fluoride.
right, right.
Okay. Fluoride is a strong ligand compared than other
Compared to, because
fluoride.
even if you will see, you can consider this as both the concepts. Either you can take it as an electronegative comp. When we are talking about
Yes,
weak
yes.
and strong, how it is going to participate in that, right? When we have a metal ligand interaction, and iron, fluorine is going to take up the d electron density because of its high electronegativity. When high electronegativity is there, that means it would be having more interaction with metal. When d electron density has been removed, that means more negative delta would be there. So maybe the question is more towards the more negative delta value compared to the more positive delta value.
Okay, ma'am.
Okay. Still, for your question, maybe the question could have been framed in a proper manner. I will get it confirmed from the professor.
Okay, ma'am.
Okay. So now we can start with a few more examples for this particular lecture. So today we have one. Last time we had an example of that nitro side example where iron is bound with the nitro group and the CN group. Here we will start with this rubritoxin. So these are different kind of complexes or the iron compounds which you will come across while you are reading some literature or finding any application or something. So rubritoxin is a tetrahedral geometry iron complex where iron is bound with S-cysteine. We have already talked about amino acids. So S-cysteine is one of such amino acids. And here so now here we have known that these kind of complexes, they involved in electron transfer. Say, for example, if I have iron in +2, it will lose one electron, will give one electron to some other moiety which can accept the electron, and it will go to iron 3. So how the MOSBAR spectroscopy is helpful in detecting whether it exists in +2 or +3 oxidation state, whether it exists in both of them, or it is still existing or maintaining just one oxidation state. So firstly, we will see the iron in +3. So iron in +3 over here, since cysteine, sulfur bound moiety would always be a weak field ligand. So it's a weak field ligand and it will form iron in +3 high spin. So that becomes in. So these kind of complexes or these kind of compounds exist in two forms, oxidized form or a reduced form. Oxidized form, that means it has lost one electron. So the metal would be in higher oxidation state. And if I'm talking with the reduced form, that means it has come back to its iron +2. So iron in 3 +3 oxidation state high spin, that's a D5 high spin. And when we have to see, now there we have to be very careful. Here it's T2 and here it's E, because we are talking about tetrahedral geometry. Earlier there was octahedral field. In octahedral field, we will be having splitting up, like T2G orbitals are having less energy, lower energy compared to the EG orbitals. That's why it was like this way earlier. EG and T2G in octahedral field. Whereas in tetrahedral field, that means having ligands surrounded in a tetrahedral manner, that would be splitting as E orbitals are lower in energy compared to T2 orbitals. So this concept is clear?
Clear, ma'am.
So when we have D5, we have to fill the D5 in a high spin. And also we know that tetrahedral geometry mostly, like there are very few exceptions where we will find the tetrahedral complexes to be low spin complexes. They will always appear as a high spin complex. So we have D5 as a splitting over here. Now you tell me, firstly, is there any valence contribution? Hello?
Not available valence contribution, ma'am.
Okay. So what about the lattice contribution?
Lattice contribution also not available.
Because of its tetrahedral geometry. So both the factors are not there. That means that iron +3, that high spin, is not going to have no splitting. One peak only, and there would be no splitting at all. One second. Okay, here actually we got little confused. Here we have the lattice contribution. Actually, what I told that if we have, just a second. So here we have lattice contribution because we are having a tetrahedral geometry. So it's not symmetrical, right? When we have an octahedral, both the upper halves, and that looks like a proper symmetrical. Tetrahedral does not seems to be symmetrical. If we have 4 ligands and if it is bound like metal, here one ligand, here other ligand, so all are at a 90 degrees and they are symmetrical. From any direction, if you'll see, it is symmetrical. Whereas if the other geometry we are taking, two are above the plane, one is above the plane, one is below the plane, and two are on the plane. So they don't look similar or symmetrical to us. So the tetrahedral geometry itself is a distorted structure. It does not come under a symmetrical structure. So that's why, because of the tetrahedral geometry, the lattice contribution exists. Do you want me to repeat it or is this clear?
Once again explain, ma'am, how lattice contribution is available in tetrahedral geometry.
Okay. So in lattice contribution, we are mainly just focusing on, if you consider a box and if all the, if I'm giving you balls or something I'm giving you and you have to put it at a specific distance and equal distance, and from any direction, if you see, it would be looking similar. For example, if I have 4 ligands and if I have to place or bind it with the metal, in which particular geometry it would look more symmetrical to you? In this particular geometry, when I am having it in a square, where all the ligands in all the directions, it would look symmetrical. Or if I'll give you a tetrahedral where one is below the plane, one is above the plane, and two are on the plane. So this will look symmetrical to you or this will look symmetrical to you?
The first one is symmetrical, ma'am.
Yeah.
Because it is in square planar shape.
Right. So in that particular case, when we have this not insymmetrical, so that means that is going to give you a lattice contribution.
Okay, ma'am. Okay.
Right. In octahedral case
I am.
also we have this kind of geometry where all the ligands, they would be like in this particular shape. So from each direction, if you'll see, it would look similar to you. Right. So that's why it is symmetrical.
Okay.
So in this particular case, the lattice contribution is existing, and therefore we have EQ, delta EQ. Just a sec. So we have delta EQ non-zero. That means splitting will occur. And now second case, if we are taking, firstly we talked about the iron +3, that's an oxidized form after it has lost one electron. So it is having delta EQ existing. What about the iron 2? That means the original reduced form, which is still having one electron. So if we are having iron 2, that is D6. Again, I said that it's a tetrahedral, so it is a high spin. Now fill this in this particular manner. Please be careful about when you are filling the d electrons where the orbitals are there. So firstly, we have filled like this. Now valence contribution is existing, lattice contribution is existing or not?
Ma'am, valency contribution is available, ma'am. Lattice contribution also available.
Because we already know that it does not look symmetrical when we are talking about the lattice. So both the factors are there. And now tell me which one is going to have more splitting compared to, so we got to know both are going to give you 2 peaks. 2 peaks would be there. I will draw that. So in this particular case, we have both valence and lattice contribution. In case of iron 3, it was only the lattice contribution existing, right? Now, first question. Out of iron 2 and iron 3, which one is having more negative delta value?
Fe +3 more negative del value.
Why is it so?
Because its oxidation state is a higher, ma'am. compare than
oxidation state is higher,
Fe plus 2.
electrons would be less electrons, the d electrons
Yes.
more shielding, less shielding. Therefore, more s electron will be penetrated. So if I am making this particular graph, we have transmittance, we have velocity, mm per second. So here we have and second one we are having right. So here this is delta EQ, value is 3.25 mm per second, and here this value is minus 0.9, this is 2.3. This value is 0.07, the delta value. This is 0.57, and the difference between these two is delta EQ is equals to 0.5. Now you tell me, green trace is your green trace belongs to which one and blue trace belongs to which one out of iron 2 and iron 3?
Fe plus 3 is is more negative, so that is minus 0.9. Fe plus 2 is more positive, that is in 2.3.
Here, firstly, we will check how are you calculating the delta values. So for delta value, we need to take as an average. So first take the average of minus 0.9 plus 2.3 divided by 2. What this value would be, it will come as 0.7. Okay. If we'll calculate, it will come as 1.4 divided by 2, that is 0.7. And this value is one value. Second, that blue trace, we are having 0.07 plus 0.57 divided by 2. And this value is 0.32. Now tell me, which one is iron 3 and which one is iron 2?
Um, 0.3 value is Fe plus 2.
So earlier,
0.7 value is Fe3.
think about it again.
Okay.
Just think about Rn plus 2, Rn plus 3. Which one is going to have more negative isomeric shift?
Plus 3 is more negative isomer shift.
If more negative.
So that is lowest value. So 0.3 for Fe plus 3, 0.7 for Fe plus 2.
Right. So delta value is 0.7 for Fe plus 2 and delta value 0.32. Right? If this is clear. Now, if this is 0.32, this
Clear, ma'am.
0.07, that means this blue trace is for iron 3 and this green trace is for iron 2. Is this clear?
Okay, ma'am.
So earlier, what you answered, how you answered, you said green trace is for iron 3, right? Now the answer is reversed. Our green trace is iron 2. So just not by looking the splitted values like minus 0.9, you saw that it's more negative. That means it. So we cannot ignore the 2.3, which is on the right side. So for delta value calculation, you have to take the average of both the values and then compare whether it is more or it is less. So is this clear how we are calculating the delta value?
Okay, ma'am, I understood.
Right. Now, this is one concept. We got to know about the delta value. But we can't ignore the splitting also, right? So earlier we saw that in case of iron plus 3, we were having only lattice contribution. In case of iron 2, we were having both lattice as well as valence contribution. So what you feel, the delta EQ 3.25 is for which one? Iron in plus 2 or iron in plus 3? Is this relatable or doesn't make any sense?
3.25.
Yeah. So more splitting, we can see that green trace is having more splitting, that is having more distance. So that appears
Okay, ma'am.
if we are having both the parameters existing or only one parameter existing.
In Fe plus 2,
Hmm.
both parameters available, that is lattice contribution and valence contribution. So it's having large electric field
Quadruple
ingredient
splitting. Yeah.
compared than Fe plus 3.
So from both the parameters, if we just see the oxidation state, there also we got to know how we can calculate or how we can predict which spectra is for what, and also looking at that splitting, that distance value of like whether the two peaks are having more splitting or it is having less splitting. From there also we can identify whether one type of oxidation state is existing or two types. So therefore, green trace is for the iron 2, that is confirmed, and blue trace is for iron 3. Iron 2 is having less negative value, or we can say iron 2 is having more positive delta value, and it is having more splitting also. Iron 3 is having less delta value and less splitting. So from this spectra, when this spectra comes from the instrument, we get to know about the true redoxine is having two possible iron, and that is one is in plus 2, one is in plus 2. How and which one is what, that we can compare and conclude. Is this clear? How we have to predict?
Clear, ma'am, clear.
Now we are moving to the next thing, another example, that is we have second example as iron where sulfurs are bound and the other positions are S16, S16,
Wake.
So here also we have iron, both are looking to be similar. So here also it's an electron transfer thing. When we have both irons over there, only one electron can transfer at one time. So in oxidized form, it would be iron in plus 3, both iron in plus 3. And in reduced form, only one electron would be transferred. So iron in plus 3 and iron in plus 2, right? Now we need to find out how the spectra looks like when we have an oxidized state and reduced state. So the delta value for this oxidized one is 0.27, because both the iron are similar oxidation state. That's why only one value is existing. And delta EQ is existing or not, that we'll find it out. Here, the delta value is 0.35 for iron 3 and 0.65 for iron 2. We have already understood that more the oxidation state, it would be having more negative delta value. That means less positive delta value. That's why iron 3 has been given 0.35 and iron 2 has been given as 0.65. Now, firstly, you tell me, earlier also we saw that iron 3, it is having a lattice contribution, because there also, if you'll see, it is a tetrahedral kind of system. Right? Two are in plane, one is above the plane, another is down below the plane. So lattice contribution is there. At iron 3, we have seen that it's Z5 high spin, it is having no valence contribution. So delta EQ is existing. So it would be having peak splitting, right? So that splitting is coming across 0.6. Whereas when we have in reduced state, one center is iron 3, one center is iron 2. Iron 2 is going to have more delta EQ because both the parameters are existing that we saw in the earlier case, and iron 3 is having one parameter existing. So still there would be delta EQ. But iron 2 would be having more splitting compared to the iron 3, and therefore the spectra will look like. So this one is for iron 3 and the outer one is for iron 2. If you'll calculate the delta values also from there also you can get to know about which one is going to give you what value. So is this clear? So how the spectra looks like when it is an oxidized state. So you can predict whether it has transferred the electron if the spectra is giving you only 2 peaks. That means only one type of iron is existing. And if it is giving you 4 peaks, that means 2 types of iron are existing. That means the complex or the compound has gone to its reduced state. So is this clear?
Clear, ma'am.
Now we are moving to the next example, which is 3 iron, 4s complexes. So these are all the complexes or compounds which we read in, which we come across in biological or bioinorganic chemistry, where they have applications in biological systems. So here, this 3 iron systems, it is just like a cubane type. So if I'll make a cube, so if here is my iron, it would be bound with one sulfur, the other sulfur. This sulfur and sulfur would bound with another iron. Here also we have iron. Here sulfur. This place remains empty and this is sulfur. And the coordination would be done by, completed by the sulfur cysteine molecules, which are outside. And this remains empty. So this kind of structure it forms 3 iron and 4 sulfur. Now again, we will be having, since these are electron transfer agents, so reduced and oxidized forms. In oxidized forms, it occurs as iron in +3, all 3 are in +3 oxidation state. All are high spin because we already know that's a tetrahedral shape. In reduced form, one would be having one electron reduction could happen at one point. So we expect generally that it is iron +3, +3 and +2. So this example is very important. So we expected it to be like this one. Is this clear? Like only one electron reduction has happened, and out of all the 3 irons which are similar to each other, so one could get reduced by 1 electron, and therefore it goes from +3 oxidation state to +2. So this is the expected. Is this clear?
Ma'am, oxidized form of iron is all are in same oxidation state.
Right.
In reduced form of iron, that is reduction. Yeah, the two F iron, the 2 iron is in +3 oxidation state. 1 iron is +2 oxidation state.
Right.
Because 1 electron is removed from, or
1
addition.
electron
Okay,
has been
reduction means gaining of electron.
Right. It has taken 1 electron. Or if you'll take the reduced form earlier, this system exists as this particular reduced form where 1 is +3, +3 and +2, and it will give 1 electron to somebody, and therefore it becomes an oxidized form 333. Yeah?
Okay, ma'am.
Oh. So now in iron 3, we know that in oxidized case here also, so here we know that iron in +3, that to D5 high spin. So we know lattice contribution exists, balance does not exist. So there would be only this kind of splitting would appear. In oxidized case, we will get only 2 peak splitting. So that is for the oxidized. But what about the reduced one? How do we confirm that iron in +3, that is 2 in nature and 1 is iron 2, and not this particular case? Iron +3, iron 2.5, iron 2.5. These systems also exist. So what actually happens? We expected that one of the 3 irons would get reduced to iron 2, and we will be having 2 Fe3 is to 1 Fe2, right? And we know that already that Fe3 is having less splitting. So we were expecting that inner ones, that Fe3 would be having more intensity compared to our Fe2. So the outer one is Fe2 and the inner one, as you can see, this is transmittance. So if you will see, suppose this is almost 2 times of your thing, like inner one, which are having the splitting, that is covering more intensity compared to the outer one. And outer one, we know that it is Rn2, inner one is Rn3. So it was expected to be Rn3 into versus 1 ratio. So is this graph clear, or should I explain it one more time? How the spectra is looking like? Why are they not looking like this way? So when I'm saying, one case is if I am having, if in case Rn3 is to Rn2, both are 1:1. So if Rn3 is there, Rn3 we know that it would be having less splitting and Rn2 would be outer one. So Rn3 would be outer one. Rn2 would be outer one. So if you will see, both are having same intensity. The transmittance is nothing but the intensity also. It is the intensity measurement. That is the case when both the Rn plus 1, plus 2 and plus 3 is existing as 1:1. Whereas in second case, if we have Rn3 is to Rn2 as 2:1. So the Rn3 is 2 times more than the Rn2. So therefore, if we have Rn3 like this way, which is the inner one, and we have Rn2, that has to be half of the intensity that we were seeing. So this intensity has been reduced. So this case becomes when Rn3 is 2 times compared to the Rn3. Now, if we have the other way, here we see that outside the Rn2s are more compared to the this one. That is the case when we have Rn3 is to Rn2, that is 1:2. These spectra are clear. How am I drawing and why am I saying about the intensity? Number of different types of irons that we are having in the complex or the compound, depending upon that, our spectra looks different. It does not always look the similar. Like splitting would be more or less similar pattern, but how the intensity, that means what is the number of that particular moiety is existing. Like if I have 2 Rn3 and 1 Rn2, then Rn3 would be having more intensity compared to the Rn2 and vice versa. So is this clear?
Clear, ma'am.
So the earlier case here, we say that we expected it to be Rn3, 3 and 2. That means 2:1. So it should look like this particular case. But actually, we got the spectra like this way, where it is not matching exactly with Rn3, 2. It is actually matching with Rn3, Rn2.5 and Rn2.5. Because we have to have only 1 electron. So half electron from here, half electron from here, the total as 1. That's why the spectra looks like this way, and it confirmed that our system, this 3Fe4s system, is existing as Rn3, Rn2.5, Rn2.5 in the oxidized state. So is this clear?
Clear, ma'am.
Okay. Now we have more or less taken all this kind of examples. One more main example that we generally come across, that's the hemoglobin example. There has been a lot of ambiguity regarding what is the oxidation state of iron. We know that in hemoglobin, iron is in deoxy form. It binds with water molecule, and there is N-histidine, that amino acid chain over here. And here we say that it exists as a +2, right? So because hemoglobin, that's in that, it takes up the oxygen and that it converts to oxygen, and N-histidine stays like this way. Now there is an ambiguity whether the iron here in oxidized form, it is in Rn3 low spin or it's high spin, and in deoxy form, this is a deoxy form, that's Rn2 high spin or Rn2 low spin. So this ambiguity can only be dealt with the MOSFET spectroscopy, and it was found that delta value for this particular system was 0.89, and for this system it was 0.23. The delta EQ was 2.23, experimentally been found, and 2.12. So what do you think? Delta value is 0.89 for the system, and this is 0.23. So what do you think whether this would be iron 2 or iron 3?
Ma'am, in oxygenated hemoglobin structure, iron having zero oxidation state.
No, zero oxidation state, it's not possible, no? Zero means it would be having like D8 electrons, that too much of 8 electrons and more shielding and less delta value, approximately it would be closing to 0. But here it is having some oxidation state. How come it would be 0? Because it seems like to be like normal, but there is a macrocyclic chain over there where the charge would be balanced, and it is existing in +2 or +3 oxidation state that I'm giving you. But I need to ask you like whether in oxy form it exists as iron 2 or iron 3, and that too in low spin or high spin. So
In
first,
oxygenated hemoglobin is
iron 2 and iron 3. Now tell me, more or less their environment is similar. So we are not talking about the ligands over here, because there also it's oxygen bound, there also it's oxygen bound. So not having much difference in oxygen or water binding to the metal system. Now see the values. Out of iron 2 and iron 3, which one is going to have more positive delta value?
Fe+2 is a more
Yeah, right. So
positive.
out of 0.89, 0.23, which one is more positive?
Out of
Out of 0.89, this value and this value, which one is more positive?
.89 is more positive, man.
Right. So now assign which one is iron 2 and which one is iron 3.
0.89 is iron 2, ma'am. 0.23 is iron 3, ma'am.
Right. So here we got to know that okay, in oxy form it's in +3. Now how do we confirm that which one is high spin and which one is low spin? So what happens really if I'll say that iron 2, generally I'm saying high spin. High spin is D6, and since it is having an octahedral kind of field, so it would be like 1, 2, 3, 4, 5. If I said that it's a high spin, so it's like this way, and it would be having valence contribution as well as lattice contribution. Therefore, delta EQ would be more, right? So this value is there. One thing. Second, if I'll say the iron 3 is in low spin. If it is in low spin, I would be having D5 low spin. So it would be this particular way. There also we have valence contribution, lattice contribution, right? So because of these two parameters, because these two are existing in both the iron 2 and iron 3, that's why the delta EQ values are more or less similar, 2.23 and 2.12. Not much difference is there. If, for example, only out of these two parameters, one parameter is existing. For example, if we'll take not the iron 3 as low spin, as high spin I'm taking, that's a D5 high spin, right? So D5 high spin would be so D5 high spin would be this line. So what do you think? Lattice contribution, we know that it's coming from the octahedral thing because the ligands and the surrounding is not symmetrical. What about the valence contribution?
Balance contribution is not available, ma'am. That is
So it is not there, right? So when it is not there, so there should be weak electric field gradient and delta EQ should be less, like very less, because only one parameter is there, right? But if you compare the values of iron 2 plus, that's 2.23,